All right, so this is the batch gradient ascent algorithm that we are going to use to find the W that maximizes our logarithm of likelihood for the binary logistic regression classification. Of course, this algorithm is an optimization algorithm that can be used for any maximization, so it doesn't need to be binary logistic regression. It's a generic algorithm that you can use for many other problems also. But all right, so far we have learned that we start with an initial guess for the vector of parameters W, and we repeat at every step. We are going to update this W in the direction of gradient, and until we don't see much of a change, and then we stop. Okay, so what is the direction of gradient? We haven't really done that yet, right? What is the gradient of our logarithm of likelihood function with respect to W, that then we can apply this method on that? So what is our likelihood logarithm of likelihood function? It has this formulation. So it's a summation over all of our data points, and then the label of the data point multiplied by logarithm of sigmoid of transpose xi being the data input data, the independent variables, and then 1 minus yi ln of 1 minus theta w transpose xi. All right. Okay, so now we want to find the gradient of that function with respect to our W vector of parameters. So first of all, we are going to use the chain rule. Just as a reminder, in chain rule, we had the derivative of f of g of x. The gradient of that with respect to x is equal to taking the gradient of f of x with respect to g of x multiplied by g of x with respect to x, right? This is the chain rule that we are going to use. Now, our likelihood function, log likelihood function, ln of L of W, looks like this. It is summation I equals to 1 to n yi ln of theta sigmoid of W transpose xi plus 1 minus yi ln of 1 minus sigmoid of W transpose xi. Okay, so first let's see what's the derivative of this term with respect to W. Okay, so what I'm going to calculate now, I'm just breaking down this problem to smaller subsets so that it will be easier for us to understand. So we are taking the derivative of yi ln of theta W transpose xi with respect to W, right? Well, yi with respect to W is a constant, so we just have yi there, right? So that's it. But for the part that is inside, let's give these inside parts some little names so that it's easier for us to calculate them. So suppose that this sigmoid of W transpose Xi, this is called Zi. And then suppose that the W transpose Xi itself, we call it Vi. Okay, just to make things easier. So here we have Zi, here we have Vi. Okay, now having the chain rule, so we have Yi, which is because it's out there. So actually, let's not do this now. Let's just take the derivative of this part, and then we will add Yi later on. That will be easier. So here, that means that we can take the derivative of ln of Zi with respect to Zi. I'm applying chain rule here, multiplied by the derivative of Zi with respect to Vi, and multiply by the gradient of Vi with respect to our W, right? Okay. So what is the derivative of a logarithm of Zi with respect to Zi? So we know that ln of Zi, ln of any variable, when we take the logarithm of a variable, we take the derivative of it with respect to that variable, is going to be 1 over that variable. So we have 1 over Zi here for the first term. Now for the next term, we have the derivative of Zi with respect to Vi, which is basically the derivative of sigmoid function. Now, the derivative of sigmoid function with respect to they're using this one also here. So the derivative of sigmoid function the derivative of theta Vi with respect to Vi, the derivative of sigmoid function, is going to be equal to theta Vi multiplied by 1 minus theta Vi. You can actually do that yourself, and it's at home. So so basically, the derivative of Zi with respect to Zi is theta Vi, right? So the derivative of Zi with respect to Vi is going to be equal to theta Vi 1 minus theta Vi, which is basically this whole thing is equivalent to theta of minus Vi, right? We know that about the sigmoid function. And then finally, we have the derivative of Vi with respect to W. So Vi is just W transpose Xi, and we have seen that before. Basically, the derivative of W transpose Xi with respect to W is going to be equal to Xi. Okay, so writing back the Zi and Vi in terms of their original format, it means that we have 1 over theta W transpose Xi, that is our Zi, right? Multiplied by theta of Vi. Vi, what was Vi? It was W transpose Xi itself, multiplied by theta of negative Vi, so negative W transpose Xi multiplied by Xi, right? So these two cancel out each other. So eventually the derivative will be theta of W transpose Xi multiplied by Xi. So what is this? This is the derivative of this this is the derivative of this ln of theta of W transpose Xi. So the derivative of this green part will be, the derivative of green part will be equal to yi dot theta W transpose Xi dot Xi. Now, if you calculate the derivative of this orange one, you can do it similar to what we have done here. Similar to this, just you can practice at home and add it. So the final derivative that we are going to have is going to be this plus the derivative of the orange part with respect to W, and then summation for I equals to 1 to n, right? Because our ln of L, our function was a summation of I equals to 1 to n. So that would give us the derivative of ln of LW with respect to W. Okay. Now, if you do calculate the orange part and you actually put everything together, you will see that this is equivalent to I equals to 1 to n yi minus theta of, or sigmoid of, W transpose Xi multiplied by Xi. Okay, so this is the derivative that we need to plug in to our algorithm to be able to calculate this batch gradient ascent steps. Okay. All right. So what is this gradient looks like? So we know that Xi is a d+1 dimensional vector because it's augmented data, right? Sigmoid of W transpose Xi. W transpose Xi is a scalar. It's the dot product of two vectors, so it's a scalar. Sigmoid of it is also a scalar. Yi is a value binary 1 or 0. So this parentheses is a scalar. Xi is a d-dimensional vector. So this derivative is going to be d+1 dimensional vector, also similar to Xi. And we know that our W is also a d+1 dimensional vector, right? So that everything matches now. So that's good. But so going back to this algorithm of batch gradient ascent, so what we are going to do is that we initialize our W, we repeat every time we calculate this derivative, going over all of our data points. So see, when we are calculating the derivative, we are going over all of our data points. For every data point from 1 to n, we calculate this value, and then we sum them up, and that will give us our derivative, right? So we calculate this derivative, and we repeat this until we get to this convergence criteria. So converging criteria. Now, this looks all right if we don't have many data points in our data set, but if we have lots of data points, if you have large data, then calculating this gradient or partial gradient at each step is going to take a lot of time for us, right? Because we are going over every data point and we are calculating this gradient, and then we are repeating this for multiple times. So that seems a little bit inefficient, right? It can be too time consuming for every step or every loop of this algorithm. So what can we do instead? What we can do is that instead of calculating the gradient for all of our data points, at each point, we pick one data point at random, And we update our gradient, our W's based on the gradient on that data point only. So instead of calculating the gradient at all x's, we calculate the gradient at one specific xi. And so we say, so instead of this with respect to instead of the gradient with respect to W, what we do is that we take the gradient with respect to we can rewrite it like this, gradient of W at some specific point xi. Okay, so which is basically ln of L of W, the same thing, but only evaluated on one data point xi. So basically, this means that instead of going this summation, we are just going to calculate yi minus theta W transpose xi multiplied by xi. So no summation there. Okay, of course, it's going to get faster in every loop because we don't go over all of our data points to calculate the gradient, but does it really get faster? Does it work? Okay. The thing is that it can be proved that actually this algorithm that is called stochastic gradient descent or ascent in this case, it can be proved that it does eventually converge to the optimum. But also in practice, it is going to be way faster than the batch gradient descent. So although it temporarily may move to the wrong direction because we are calculating the derivative with respect to one data point instead of the whole data set, but eventually it's going to get faster. And also it's easy to parallelize this whole algorithm. So that also adds, it helps more to get things done faster. Okay, so basically, in stochastic gradient descent, and it is stochastic because we are choosing one data point xi at random, and then we update the gradient like this, update the W like this with the gradient at that specific data point. What we do is this. So this is the algorithm for logistic regression, binary logistic regression with stochastic gradient ascent. What we have is that our input is data D, and this is, if you remember, it's a step size or learning parameter that is also an input to the algorithm. You set it, and also this epsilon that is going to help us to decide when to stop iterating. So first of all, the first thing that we do is that we add a 1 to each of our data points to make our data points augmented, to not to treat biases separately. And we calculate the iteration. We set the iteration to be 0. We initialize our W or weight vector. So it can be initialized as 0, it can be initialized at random, or if you know something where the W is going to fall, roughly you can initialize with that. And then we are going to repeat. In each iteration, we first copy the vector W of the previous iteration that we had, we keep it. And at random, we choose a data point xi, random. And then we calculate the gradient of our log likelihood with respect to W at that data point xi. And we update the W vector. We do this until we go over all of our data points in a random order. After we have done this, we update, we say, okay, the last iteration there is going to give us the W for large iteration counter t plus 1. We update WT plus 1, and we set the counter to t equals to t plus 1. And we do this, repeat this large iteration until we get to convergence, meaning that the W's change much. So their change is less than or equal to a value epsilon that we have given as the input. So you see that the outer loop is basically the same as the batch gradient descent. The only difference is that in the inner loop, instead of calculating the gradient once for everyone, we are looping over our data points at random, and we calculate the gradient one by one. This is one way to do stochastic gradient descent. Another way that people do it is that instead of selecting xi's at random every time, they permute the data points. So in our data, we have an order, right? There's an x1, x2, etc., xn. And what they do, they shuffle the data. So what you can do in practice is just to shuffle the data. So for example, we get x10, x1, x14, etc., x9. And then we go over the data points one by one. So it doesn't matter. You can shuffle or you can select at random. The reason that we do this selection at random in practice is that if there is an association between our data points because of their order, for example, suppose that you are recording your data points in time. So there is a sequence, kind of time sequence in your data, and you guess that maybe there is an association between the data points in the sequence. For example, there is a variable that increases roughly in this time sequence, but we don't want that to happen when we are training our algorithm, because we do have this assumption of independence between our data points. So to break down the potential associations that may exist in the data, we shuffle them, and this way, or we select them at random, and then we are basically breaking down that hidden association, and we get closer to an IID sample. All right, so this is the algorithm for logistic regression. Now, okay, how can I do prediction with that? Suppose that I did this algorithm and I learned a W vector. That the algorithm is telling me this is the best W vector that you can get according to your data points. How can I do prediction with that? How can I find the class label for a new data point with that? Okay, so what we do is that given that W, we can calculate the pi of xi. You remember that when we began this session, we said that probability of yi being equal to 1 given xi is going to be equal to pi of xi, which was, we defined it as theta of W transpose xi. And the probability of yi being 0 given xi was 1 minus pi of xi, right? Which is 1 minus theta W transpose xi. So if someone gives me a new data points, so suppose that I call this new data point z, instead of xi, I'm given a z. because I know W, I have learned my W according to my data. What I can do is that I can calculate W transpose Z, and I can calculate theta of, or sigmoid of W transpose Z, and that is going to be the pi for Z, right? And I can basically look at the value for pi for Z. If this value is larger than or equal to 0.5, equal just is a convention, then it means that the probability for y being equal to 1 is more than the probability of y being equal to 0, right? Because if, for example, pi of z is 0.6, that is the probability of y being equal to 1, right? Is 0.6, the probability of y being equal to 0 is going to be 1 minus 0.6, which is 0.4. So I would say, okay, the class label is probably 1 because the probability of y being equal to 1 is more, right? So if the theta of W transpose Xi is larger than or equal to 0.5, I would say the predicted class label is going to be 1. Otherwise, if it's less than 0.5, meaning that 1 minus that is larger, then the class label that I predict is going to be 0. Okay, so that is how we are going to use our classifier that we have learned based on binary logistic regression to predict our class label for a given data point, any given data point.